Assuming that you have access to some kind of calculator or graphing tool, evaluating exponential models shouldn't be too difficult. You just type the appropriate numbers in. The real trick for solving exponential model problems by hand is actually being able to write the equation in the first place. So I have actually three different types. These are the ones included in our textbook for pre-calculus. The first type of exponential model is compound interest. In this formula, we're actually compounding interest a certain number of times per year. The letters here, A stands for the amount that you'll have when you're done. P is the principal, that is the amount originally invested. We have a rate, a percentage rate, R. And then N is the number of times per year. So if your interest is compounded monthly, N would be 12. Whereas if your interest is compounded only quarterly, that's 4 times a year, so N would be 4. T then is the number of years. We're also going to do an example where we have growth and decay. We have here a yearly percent growth rate. It's very similar to the compound interest formula, except that since we're doing it we're basically compounding once per year, our annual growth rate, there's no N involved. There is a function for continuous growth or decay, and this function actually applies to continuously compounded interest as well. Your book, the book we're using, and a lot of other books will actually use an interest version of continuously compounded. So this is continually compounded interest. Notice the natural number pops out. That's just a result of increasing the number of compounds toward infinity. In my experience, though, you're unlikely to find a situation where somebody is going to credit you interest continuously. It's a little ridiculous from a financial perspective, but it does lend nicely into certain situations where there's so many of something that it's better to just think of it as continuous growth. Now the K here, instead of R, K is meant to stand for a continuous growth rate. So the numbers are going to be a little different, but you can think of them percent-wise still. So here we have the amount we'll have at the end, N0 or N0 is the amount we had at the beginning. Again, we have the rate. Now, if you have a decay situation rather than a growth situation, R will be less than 1. And so this term will actually be, R will be less than 0. It'll be negative. So this term will be less than 1, which is what's going to produce your decay function. And the same thing will happen here, except K will be negative. So you'll end up with a decay function rather than a growth function. As far as applying these formulas, I have a couple of examples to work through. This will help you get started, but really, as with word problems, approaching the problem, trying to understand the problem, fit it into your situation, it takes practice. Rather than, I can't just tell you how to do all problems of this type. So in a situation which is pretty straightforward, we're going to invest $2,000. We're going to get an interest rate of 5%. We're going to invest for 18 years. We're going to figure out how much money we have based on how often they're going to compound the interest. So our formula has a spot for each of these. The amount we have at the end, the principal, which is how much we invested, interest rate, number of times it's compounded, and how long. So the information in the main part of the question includes the principal of $2,000, the annual interest rate of 5%, which we need to write as a decimal, 0.05, and T, the number of years, which is 18. When we're compounding quarterly, N will be 4. Now you could simplify the inside here, but I find we're better off just to head straight to a calculator, which I forgot to grab. One moment. So since I'm using my computer to record right now, rather than use a calculator on it, I'm just going to pull out my TI-84 Plus calculator and put this in. Like I said, we could do the middle and build it one piece at a time. I find I'm more likely to make errors as I start spreading it out. But I also have a lot of experience typing these in. So if you would rather do it in pieces, it's fine with me. Make sure both of these numbers wind up in the exponent. Otherwise, you don't want to multiply 18 at the end. You want to make sure that 18 is in the exponent. So 0.05 divided. All right, so our quarterly number is $4,891.84. That's how much we'll have if we compound quarterly, 4 times a year. If we change this to compound monthly, what changes in the formula is n. So we'll have 1 plus 0.05 over 12, that is 12 times per year. So the base will get smaller, but so will the exponent, because instead of 4 times 18, so we're compounding less each time, but we're compounding more often. So if I come in here, I change this 4 to a 12, and I change this 4 to a 12, I will get a little bit more money, $4,910.02. Notice the money's gone up a little bit, although the amount of increase there, what, 20 bucks, a little less, is hardly compelling. If I do interest compounded daily, I'll make even more money, although the amount of the increase will actually be even less, I suspect. So 365 days in a year, 365 times 18. So if I go back in and change this one to 365, and change this to 365, I will have $4,918.90. So an extra almost $9. This is one of the reasons you won't find people compounding interest continuously, is it barely makes a difference. I've never had an investment that did anything besides monthly. But on the other hand, I've never invested a lot of money. So right here we have, this is the compound interest formula based on how often you want it to compound. In situations that are not financial, you may want to use the compounded interest formula if, I don't know, you were measuring the growth of something, but you measured it like every month rather than once a year. Most of the situations you're going to see in textbooks will involve an annual growth rate that's just kind of assumed to be once a year. So here we have the magical kingdom of Barnardia has a population of 1.1 million inhabitants. If the population declines at a rate of 2.6% annually, how many inhabitants will be left after 15 and 30 years? So here we can see this is a decline of 2.6, which tells me right away that our rate of decay, is going to be negative 0.026. Don't forget to turn that from percent form into decimal form or fraction form. You could do 26 over 100 if you really wanted to. The original amount I also know, so that's going to be n naught or n sub 0, and it's 1.1 million. I'll write it out. Million. Okay. 1.1 million. And the specific question I'm answering is going to tell me what t is supposed to be. Our yearly growth rate formula is this one, 1 plus r to the t, which is even simpler than our last example. But the amount we have left at the end is going to be 1.1 million times 1 minus 0.026 to the 15th power. And there it's calculator time. This one's a little easier to figure out the base, 0.974, but it hardly matters if you don't want to do that. 0, 0. So 1.1 million times 1 minus 0.026 to the 15th power. So 740,000, 741,000-ish. I suppose this is math class and not science class. So I will report all of these digits, even though anybody who's got a passing familiarity with precision will tell you that this number is ridiculous. I should say all those digits are ridiculous. Ooh, 929. So somewhere around 740,000 is what we're looking at after 15 years at losing 2.6 per year. If I'm doing 30 years instead, the only thing that actually changes is my exponent becomes 30. And after 30 years, I'm down to about 500,000 inhabitants. I'm not including those decimals. All right. So about 500,000 after 30 years. See, it takes a while to get low. The lower it gets, the smaller 2.6 of this number is, and the slower the growth rate. That's how exponential decay works. If you remember the equation, the graph, it looks kind of like this. So the lower it gets, the less you're losing every year. There it is. We have the three formulas. I guess I didn't use the continuously compounded one, but on the other hand, sticking this stuff in the right place, it's got all the same features. You'll want to use a calculator and get decimal approximations for these most of the time. This is the best I got for you. If you have specific questions about a problem that you'd like to see me do, just let me know.